So our next speaker will be Moul of Condor Consulting, and he'll be talking about gravity data.
All right. I guess the first thing to comment on is the title of my presentation. I know we're talking about the Athabasca Basin, but there's kind of a paucity of good public examples of gravity anomalies associated with mineralization in the Athabasca, and really the best case we've got to look at is the Kiggavik deposit in the Thelon Basin. So I put in the Thelon as well, just so you can see it. And it's a good analogy for what we might see in a similar context in the Athabasca. Do I go forward? All right, so just to orient myself, I guess, as well as everybody else, I went into the assessment archive and I just put in a few queries. I looked for things like full tensor gradient, FTG, AGG for airborne gravity gradient, Falcon, the proprietary name for BHP's AGG system, gravity, and I pulled out the airborne and the ground assessment files. So, you know, the areas these polygons indicate for the assessment files don't necessarily directly relate to the survey areas, probably over-representing the amount of data. But, you know, it gives you a sense that there's a lot of gravity data that's in the assessment archives. I didn't restrict the query to relatively new data sets, say within the last couple decades, which are likely to be digital. This would include paper maps and archives as well. But there's a lot of data, particularly in the eastern part of the basin. So I guess the point of this is, if you find value in the gravity data, there's a huge historical reference, and the gravity data doesn't particularly go stale. It only improves as we get better constraints, and so incorporating the historical data with anything new that's acquired, or looking at it prior to acquiring new data, is a valuable exercise. I thought I should put something into contrast with the magnetic data acquisition. So I took the Athabasca 200-meter compilation on the upper right, and that's the Canada Bouguer compilation at 2 kilometer south spacing on the left. I didn't have a polygon of the Alberta side of the basins, so I apologize if anybody's interested in that bit. So the main thing to note about gravity versus magnetic data is that we don't have the complication of remnants, we don't have the complication or perhaps the added information that comes from remnants or dipolar responses. It's a monopolar response. You know, we've got an increase in the acceleration due to gravity in the direction of the relatively dense source. So we're looking at excess mass anomalies, and it's relatively simple to treat as a potential field compared to the magnetic data. However, acquisition of it is relatively difficult, and so the resolution of the data is pretty coarse, and it is difficult to use often on a project scale unless you've got a project scale survey. One thing that I'd be concerned with initially is if we're in the basin and we've got you know, greater than 1 kilometer's worth of sandstone, and unlike with the magnetic technique, the density variations in the sandstone can cause gravity anomalies. So if we're just looking at, a regional gravity survey, are we looking at the depth to the unconformity primarily? And this is a depth to unconformity map for the basin. As we can see, I think there's a much better correlation of Bouguer gravity here with the magnetics than there is with the basin depth. So we get real lithological data of the gravity. We also get some sense of unconformity depth. Also, there are differences between the gravity and the magnetics, which are useful potentially for mapping. We can have dense features that are magnetic lows, excess mass features that are relative mag lows, or we can have the reverse. This helps us to map the units on a regional scale. So somewhat like OMID, I pulled this chart from the Mineral Deposits of Canada. So under gravity, we're saying that we've only got 2 categories here. We've got essentially direct detection and geologic framework. And I think we kind of omit the detection of alteration that's directly associated with mineralization. That's one thing that we have we can use gravity for in the basin is sort of this intimately associated alteration features. So in this chart, we're saying that generally gravity is ineffective for direct targeting. Well, I think there's a bit of gray area there. I think we can argue that both high-resolution airborne surveys and ground data could be used to find alteration associated with uranium mineralization, and that alteration could be fairly intimately tied to the mineralization. We can also use it to improve the geological framework, where we might find permissive areas for mineralization. In this case, they've said that airborne data is moderately effective and ground data is highly effective. I think, we're able to acquire fairly large gravity data over fairly large areas from the air, which can be of great assistance for design or identifying the geological framework for a deposit. It's very costly to do the same thing on the ground. The data is higher fidelity, but perhaps acquiring similar resolution is very costly. So I think that the relative weights of moderately effective from the air and highly effective from the ground could maybe be evened out. It all depends on the context of the project. Okay, so we've seen this figure before. Two types of uranium deposits in the basin formed by either hydrothermal fluids coming out of the basin coming out of the basement or into the basement, mineralization forming in the basement or at the unconformity, or a mixture of the two. And the endpoint models then being an egress type mineralization and alteration halo at Cigar Lake, ingress type at Eagle Point, and a mixture of Key Lake and the Dillon ore body. Another thing that's important for gravity, I think, is at Eagle Point we've got a real difference in the competency of the units on either side of the fault. And that could be potential geologic framework, structural target that we could use to locate uranium. And we were able to see units of significant density, which may not have a magnetic contrast. I guess a bit of an aside. When I was putting this together, my initial thought was I would dig into the assessment file and find some interesting cases in the public data. I didn't really have time to do that. I thought, I could introduce the acquisition. There's all sorts of interesting airborne systems out there. There's all sorts of permutations of why particular approaches to acquisition are better for different cases. There's also lots of information about processing we could talk about. And those are all pretty interesting problems to me. I enjoy the processing, enjoy the modeling, but really I think that stuff we can get out of textbooks or publications that already exist pretty easily. It's all compiled into single volumes, and the interesting stuff is talking about actual examples of data that are over cases of mineralization. So that's what I plumbed the documents that I could find and trying to present that here. And one interesting bit of work that was done was by Jonathan Mutafumbo, and they did a series of borehole logs. And I think some of this was in the X-Tech volume, but I pulled a table and a chart here. The table refers to both the McArthur River and the Shea Creek areas. This chart is just from Reed Lake, which is, I guess, so close to the McArthur River. And the interesting thing that he shows, for me, is that there's a general increase in density as we go through the Athabasca sandstones. So I think we're looking at a decrease in porosity, and therefore an increase in density. And there's a significant jump when we get close to the basement and then in the basement rocks. So the variation in all units listed in McArthur River and the Shea Creek area is about 0.3 and 0.2 grams per cc, which I think are useful numbers to keep in mind. We've got this kind of natural lithologic variation in the densities without alteration could be a factor in some of these measurements, but really in the host rocks. So what are our target types we could apply gravity to? one I take to be the alteration in sandstone. So above the deposit, we've got either silicification, desilicification, corresponding to increases or decreases in porosity, and those are going to result in nominally minus 0.2 grams per cc change in density for desilicification and plus 0.2 grams per cc for silicification. So it's not a really big density contrast provided for us by the alteration, but it is in the sandstone, which is relatively close to our point of measurement. This figure down here, I think, was based on recognition of this at Key Lake, and they did, I think he says hundreds of measurements in the text, and the model they came up with there was a minus 0.15 grams per cc. So, you know, I think we just use a rough number when we're saying minus 0.2 or plus 0.2. But the idea here being that the alteration is above a fault zone, the mineralization is at the unconformity in this case. The alteration chimney rises towards surface and it's being truncated by overburden. So we've got the problem of seeing through the overburden, seeing through lakes, but we have this small density difference that can extend over a large volume of rock directly over the deposit, potentially. We've also got the density contrast between the various gneissic rocks. A few years ago, Condor did a experiment, I suppose, just to demonstrate the efficacy of using airborne gravity gradient data to find this alteration zone in the sandstone. And this is the Black Lake area. So a sandstone alteration body was generated here, placed under 25 meters of cover. This parametric model, and then various density contrasts were provided for the body, and it was stuck inside of a real set of Falcon AGG data. And then in each case here, you can see the block without the bodies placed and the block with the sandstone alteration. Sorry, so it's not actually the mineralization, but it's the alteration. So it's present here, absent here, and there's a cross section between each. And so you can see that there's, in the data, just looking at the gridded data or in the inversion, there's a clearly resolvable anomaly associated with particularly the higher density contrast. So where we've got alteration chimney of those sorts of plus or minus 0.15 grams per cc under 25 meters of cover, it looks like you can see it in airborne gravity gradient data. All right, so that's one target type. The other target type then is looking for sorts of features which might enhance the flow of hydrothermal fluids at the unconformity or in the basement. And so we've got Colin's map. I use this a lot on the western side of the basin because there's a real absence of basement geology data. But you know, this is kind of a catch-all category. We can imagine what we think might be represented by the data, what might be permissive in a given area, and we can throw it in there. So we've got these quartzite ridges. We've got vertical displacement along faults, as we see in McArthur. I think there's also the quartzite issue. Paleo channels, I don't have a case for that, but it seems to make sense. If you see a low point in the basement, this might be something of interest. Contacts with rocks between different competency as an equal point. Impact structures, I was at Carswell. I put pass field in there just because we have data over it, though I know it's a controversial topic whether that's an impact structure or not. Yeah, so I think, what do I have got for examples? I guess that's it for the two target types. So going to the first type at Kiggavik, way up here in the Thelon Basin. This, I don't actually know the geology that's represented here. I was just using this for location of deposits. So I'm going to talk about Kiggavik and Andrew Lake. Andrew Lake first. Kiggavik first. Okay. So in this case, we've got the mineralization located next to a granite body in some, this is an orphan quartzite in the metamorphose, inside of the sedimentary rocks. So the mineralization occurs in the basement rocks, principally in the metasediments near the unconformity. And there's intensive clay alteration around the mineralization. There's two different sections presented here from a different vintage. You can see that the deposit was expanded down dip in the 2005 image. And this granite wasn't really defined in the earlier one from 1990. But I put this one in because it shows this zone of desilicification inside the ore zone in this case. And they've defined it as minus 0.24 grams per cc, which is significant enough response. It appears to be resolvable. So this is, on the left we have a model section. This isn't a real geologic section. We put in a minus 4 grams per cc density contrast in order to model the observed gravity load over the deposit. And here you can see it's a very nice concentric low, which is centered right on the mineralization. And then if we look at Andrew Lake, we've got slightly better images to work with. The total range, as presented on the color bar here, is a little less than 2 milligauss. And if we look at this chart here, these are the different ore lenses. This is a resistivity low, and the green is the gravity low. Over here we see the grid of the gravity low with the growth pattern, and that's about a minus 0.7 milligal. It's easily resolvable, provided we've got reasonable data. Just down here we're showing alteration payable around the mineralization. Okay, at Key Lake, I threw this one in, and I found this, I didn't recognize the parallels between this discovery and those in the Patterson corridor until recently. But it's a pretty neat deposit, and we do have a tiny bit of gravity data over it that I thought was pretty informative. This, I think, is it's a schematic cross section. I don't know how much real data went into defining this, but here we see the orthogneiss, paragneiss. There seems to be a fault here with some, it's a reverse fault with some significant vertical displacement, and the ore is here perched at the unconformity. It happens to be in relatively thin cover just inside the basin. And we've got some data over the Gaertner ore zone. Again, this is an interpreted section, not real data, and that's perhaps why it matches up so well. The gravity profile on the top, let's pick the inflection points here. And so that's where they've defined the edge of this granite dome and these metasediments. And then in the magnetics, we're defining what's interpreted to be another granite, perhaps a more magnetic granite on the flanks. So where the metasediments and the granite are being lumped into one unit based on the magnetics, gravity seems to be defining the granite dome, and the body is perched just at the edge of the granite dome. And the gravity profile they showed I thought was pretty nice, because they state there's a minus 0.3 milligal anomaly, and I just drew in my own regional here. And it's a really tiny little dip on this profile. But it's arguable that 0.3 milligals is real. It highlights the importance of understanding what the regional is in the area. If there's another reason to cause that very small dip through an increased depth to the basement, perhaps in that area, this certainly wouldn't be indicative of any sort of any object of interest. And if we don't have constraints and we don't have a good idea of what the regional gravity looks like, we can't really identify these small features. So McArthur, there's this in the well, there's been a couple of generations of models that have been done here. The schematic representation is that you've got this quartzite body, you've got a reverse fault, a P2 fault, and mineralization that is along the fault and along the unconformity lineage of the basement. So here's a real geologic section. You can see this, I think the blue represents an alteration zone. So it's moderate silicification, strong silicification. So I think the degree of silicification is decreasing as we get further from the ore zone. So this is Gaertner's work from 2002, and I think the main point they were trying to make here is that the regional data is really very sparse, and it's not very useful. The transect that went through the deposit area was able to identify clear a response which appeared to be related to quartzite, and there's some higher frequency features over top of the area of the deposit that aren't easily defined. So the first generation model then modeled those quartzite ridges as these local highs. Then, with the seismic deflection work that was done, there's, well, actually, it's important to note the depth here is just about 200 meters. Here we have a geologic interpreted section down to 5 kilometers supported by the seismic work. And then we've got the gravity over the area. Go on to the next slide here. And zoomed in over the area of the deposit here. I should do that. You can see, we don't have the profile on the next slide. So you can see the profile represented here. And we've got much, much better constraints now to explain these fairly small highs and lows. And given the lack of really good regional data, we're able to estimate what a reasonable regional is based on the seismic section. So if we look at what was placed directly above McArthur, we end up with a silicification causing a 0.35, 0.05 increase in density. All right, and the last case I've got to talk about is over Arrow. There's, this is Patterson Lake South corridor in here, just at the edge of the basin. There's a number of deposits. The only one that I've really got data to show for is Arrow. An important factor here is that it's surrounded by Patterson Lake, which is pretty big and pretty deep. And it's important to constrain this when we're looking at the gravity data, because there really are huge anomalies related to these near surface to the lakes, because there's a big density contrast there. We've got about 2.67 for mean crystalline basement, I guess, and maybe 2.3 for the sandstones, and 1 for the water. And it's right at surface, and when you do a forward model of the lake, you get a huge anomaly relative to what we might see from alteration around the deposit, 2 milligauss. In the gradients, it's 50 atlas. And the shape of the anomaly pretty much directly corresponds to the shape of the lake bottom, which we, without good bathymetry data, we have no idea. So here's the deposit, relatively near surface. It's surrounded by gneisses. It's situated directly against an ortho-gneiss body, vertical lenses. And there's not too many public images we have, but this one's from 43101. It says that the discovery was partially the result of drill testing of circular gravity and low anomaly, which is presented here. It's about 1 milligal, which is fairly significant. And in the inset, they show the larger ground gravity survey. And I think this is actually the Bouguer, likely the Bouguer gravity. We don't have anything to support that really, except it doesn't look like a residual to me. And it correlates pretty well with the residual data from the airborne survey, which was flown in 2016, I think. There's an error in the units in each of these plots. I think this must be that close. But we end up with a gravity low over the deposit, lows over some of the other deposits as well. And in general, conformation in the shape of the field from a high in the west, northwest, and lower in the southeast. This is a residual of the ground gravity data, and that low is still present, and just similar to the previous map, I'll zoom in, about 1 milligauss difference from the highest to the lowest. Okay, I don't know, this was kind of a stream of consciousness thing. You might prefer to just read it in the notes, but I think a lot of the problems we have with gravity data can also be benefits to us. I mean, some things improve with time. The noise gets better as the systems get better. Our lack of constraints are a problem, but as the data mature, we get more constraints. You know, like this seismic deflection data at McArthur, like better bathymetry data. And so the data can remain useful even if at the time of acquisition we aren't able to do robust interpretation. I think we can as time goes on. The poorly constrained conformity depth could be a problem, but if we can see, if we make an argument for actually resolving the shape of the basement, this could potentially generate targets. If we poorly constrained densities are really a problem, but the only way we can overcome that is by sampling the downhole logging. Sparse regional data is a real problem, particularly when we're trying to merge AGG data sets, because the regional in older surveys anyway is really you take two overlapping AGG data sets and they just don't conform. So we need some way to conform the data to a common reference, common regional reference. New surveys with the Falcon system include a gravimeter, which should allow them to do better, generate surveys which conform better. But when you're pulling historic airborne data out of the archives, you may find that they just don't match at all, and this is a genuine issue. Yeah, and the real problem is the relatively narrow range of densities that we have associated with the target type unit. That's 0.2 grams per cc plus or minus is not very large compared to the potential density differences there in the host. Yeah, so I was wondering, why is there so much gravity data, particularly airborne gravity data, in the assessment record if we've got all these problems? And I think the main driver at this point is that the basin's been really thoroughly surveyed with magnetics. We've got incredible magnetic data sets. We've got multiple generations of time domain EM coverage. We're starting to get Z10 coverage, but we don't have all that much gravity data at resolutions that are useful on project scale. So if you've already got all this data and you want to fly an airborne survey, then flying a gravity survey can make a lot of sense, despite all the inherent complications. It's, you know, and because it's an airborne survey, it's basically turnkey. You don't need to have a camp necessarily. You don't have to have people in the field. There's a simplified process of essentially spending your exploration dollars and getting assessment credit. And as I understand, there's additional benefits for doing airborne, or additional credit for doing airborne survey. So I think we should see more AGG. There's some summary. I'll leave that slide at the conclusion so we can basically not anything. There's a bit of time for a question.